Okay, good evening. This is week 2 on a Tuesday. Today's agenda, I'm going to finish off on centric symmetrical bending. Then I'm going to go into centric unsymmetrical bending. And more important is, what do you mean by symmetry and unsymmetry? What does it actually means? Okay. Then I'd like to announce quiz 1 will be available on May 16 and will be based on homework 1 and 2, 75 minutes duration in quizzes, and can be 75 minutes duration. It can be found in the quiz module on Avenue to Learn. Due date is May 20th. Okay, so that is quiz number 1, and I think the most important thing to know is from homework 1 and homework 2. I hope to post homework 2 tonight. Okay. So let's finish off on centric symmetrical bending. Okay. So before I go there, what did we do last week? Last week we finished off on me helping you to recall on your shear force and bending moment diagram and the relationship with shear force and bending moment. Like for example, if the magnitude of the shear force is positive, the bending moment gradient is positive. When it's negative, the gradient is negative. And when the shear force intersects 0, there is a possibility for the bending moment to be at its maximum. But more important, just to quickly recap regarding bending moment at this stage, the more important part is whenever we have a bending moment vector, the head will always be compression, the tail end of the bending moment vector will always be tensile. Okay, so that's just a quick recap on what we've done. So now, why do we say a structure, or why do we say that a structure is centric symmetrical bending, okay, or under centric symmetrical bending? Whereas under centric symmetrical bending, we are aware that the formula to use is stress in the x direction is equal to mz over izz multiplied by y, and usually we have a negative sign in front of you. So I'm going to draw two structures now. Okay. So one of it, both of it will be simply supported. Okay. So this is one of the structure. Okay. So this is on one side, it is pin. On the other side is on a roller, and you have point A and point B. Then I'm going to have this structure that is under evenly distributed load. Okay. So you can see you have omega Newton per meter. So we classified this as a evenly distributed load. Then I will draw another structure by the side. Same thing, simply supported. Okay. And again, a pin and a roller, point A, point B. And at a certain distance, we have our point C and a certain distance, we have a point D. Okay, but this time the load is different. Okay, one side you have a gradient distributed load, and then at point D you have a point load. So down here we have a gradient distributed load, gain omega Newton per meter, and then at point D you have a load P. Okay, so you also have a point load. Okay, so you can see two beams are not loaded the same way. Okay, so one on the left hand side, the beam is loaded evenly distributed. On the right hand side, you have a beam that has a gradient. Yeah, I spell my gradient wrongly. A gradient distributed load, and you also have a point load. Okay, so at this stage, do we know which structure is under symmetrical bending? Anyone? Is it the one on the left or the one on the right? Can anyone tell me before I do that? They both comply to a transformation that you have X and Y, and this is rotation about Z. Okay. So we have structure number 1, structure number 2. Can anyone tell me which one is under centric symmetrical bending? 1 or 2? Anyone? You can type. I can see your answer also if you want to. I have no reply over here. Anyone? Anyone there? Hello, can you hear me? Am I hang? Number 1. Okay, so I thought I'm hung. Okay, I don't see any messages. Okay, so the thing is, we can't tell from here. And Lucia, I understand why you say number 1, because based on geometry and based on loading. So why we say number 1? Okay, and I will have guessed. My answer will be the same as Lucia. I will have said number 1. This is because if is based on loading or loading condition and geometry. Number 1 is under symmetrical loading. I highlight down here. This is known as symmetrical loading. Okay. Yep. Yeah. Absolutely right. Why? Because the AY is equal to BY. Okay. AY being the reaction at point A, BY being the reaction at BY. Okay. So let's say we have our reaction down here. Now, unfortunately, from the loading condition and geometry, okay, we cannot classify whether the structure is under symmetrical bending. Okay, symmetrical loading, yes. Okay, 1 is under symmetrical loading, but whether it's under symmetrical bending, we can't tell from here. Okay, let me elaborate. Okay, now I'm going to draw the cross-sectional area of the structure. Okay, I'm going to sketch the cross-sectional area of the structure. Okay, so we have so I'm going to view differently now, or we are going to view differently now. So this is our y, and this is our z, and this is our rotation about x. Okay, and then we are going to sketch cross section number 1. Okay, so cross section number 1 looks like this. Okay, and then I'm going to sketch cross section number 2. So this is cross section number 2. And then I'm going to sketch cross section number 3. Okay, so these are the cross-section view, and then at all these points I'm going to label them. Okay, on the top left hand point is always alpha. Okay, all these are alpha. Then the top right hand will be our beta. Then bottom left hand will be our I. And this is our J. And then I'm also going to sketch the centroid on both along the y-axis and along the z-axis. So I'm going to sketch the centroid. Okay, this is just a sketch. Okay, so this is one centroid axis, and this is the other. This is one centroid axis. This is the other. Then this one is straightforward. It's exactly at the center. Now, from the cross section, okay, can anyone tell me which one is under symmetrical loading? Cross section number 1, number 2, or number 3? Anyone? If, okay, let me further elaborate. If the acting moment for all of them, hold on, not if, when the acting moment or when the moment is applied on the z-axis. Okay, so the most important thing to look at, if that's the case, is the centroid on parallel to the z axis. Okay, so these are all the centroid. Okay, can anyone tell me which one or before anyone tell me, and I want you to focus on the formula where stress X is equal to